Welcome to the first of several videos on applications of extrema of functions of two variables. The goal of this video is to determine the minimum distance from a point to a plane. In order to solve these types of problems, once we determine our function in terms of two variables, we'll follow the same steps we followed to determine the relative extrema of functions of two variables in a previous video. So you may want to pause the video here to review these steps. For our example here, we want to determine the minimum distance from the plane 3x minus 2y plus z equals 6 to the point 0, 0, 0, which is the origin. So we're trying to determine the minimum distance from the origin to this plane, which we could represent as this red segment here. Remember, the distance between 2 points in space is given by this distance formula, so we want to minimize this distance. But instead of using this distance formula, if we were to square both sides of this and then call little d big D, we could minimize the square of this distance formula and therefore eliminate the square root. So we're going to use the formula big D is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared instead. So let's see if we can come up with a function in terms of three variables and then somehow rewrite it in terms of two variables, given that one of the points has to lie in this plane. What I mean by that is we could easily solve this equation for z in terms of x and y, and then we could have all three coordinates in terms of x and y. So if we solve this equation for z, we would have z equals 6 minus 3x plus 2y. Now the reason that's helpful is, going back to the square of the distance formula, we can now rewrite this as big D is going to be equal to x minus 0 squared plus y minus 0 squared plus z minus 0 squared, but z is equal to 6 minus 3x plus 2y minus 0 squared. So now we have a function big D in terms of two variables, x and y. Let's go ahead and clean this up a little bit. So we'll have big D is equal to x squared plus y squared plus 6 minus 3x plus 2y squared. So now we'll take this function and determine the relative extrema. Remember, what we're going to do is determine where the first order partial derivatives are equal to 0 or undefined, and then determine the value of D, and based upon those values we can determine whether we have a relative min, relative max, a saddle point, or the test is inconclusive. So the partial derivative of D with respect to x would be 2x, this would be 0. Here we'll have to apply the chain rule. We're going to have 2 times 6 minus 3x plus 2y times u prime, which is going to be negative 3. Let's go ahead and simplify this. We'll have 2x. Here we have negative 3 times 2, that's negative 6. So we'll distribute negative 6. It'll be minus 36 plus 18x minus 12y. So the partial with respect to x is going to be equal to 20x minus 12y minus 36. And we want to know when this will be equal to 0. Now let's determine the partial derivative of d with respect to y. So we're going to have 0 plus 2y plus, again, we have 2 times 6 minus 3x plus 2y to the first, and then times 2. Let's simplify this. We're going to have 2y. We have 2 times 2, so we'll distribute 4. So plus 24 minus 12x plus 8y. So we have the partial derivative with respect to y would be equal to negative 12x plus 10y plus 24. And we also want to know when this is equal to 0. So what we'll do now is treat these as a system of equations and solve for x and y. Let's go ahead and do that on the next screen. Okay, so what I'm going to do here is move the constants to the right side, and I'm also going to divide this first equation by 4 and divide the second equation by 2. So if we divide by 4, we're going to have 5x minus 3y. Divide this by 4, it'll give us 9, so we'll have a positive 9 on the right side. And now we'll divide this equation by 2 and move the constant over, so we'll have negative 6x plus 5y equals negative 12. Now we'll use elimination to solve this system. We'll eliminate the y terms by multiplying the first equation by 5 and the second equation by 3. That'll make the y terms negative 15 and positive 15. So we'll have 25x minus 15y equals 45. The second equation will be negative 18x plus 15y equals negative 36. That's 0. We'll have 7x equals, this will give us 9. So x is equal to 9/7. Now let's go ahead and determine y by substituting x equals 9/7 into this equation here. So if we move the x term to the other side, we'll have 5y equals 6 times 9/7 minus 12. So give us 5y equals negative 37. Multiply both sides by 1/5. So we have y equals negative 6/7. Okay, so we have x equals 9/7, y equals negative 6/7. We should probably go ahead and determine z. Remember, we had an equation for z on the other slide. We have z equals 6 minus 3x plus 2y. So let's go ahead and determine z while we're here. For the sake of time, I've already determined this. It comes out to 3/7. So what we have so far are the three coordinates that we think will minimize or maximize the distance between the plane and the origin. But to be sure, we should take the time to determine the value of d as we see here and make sure that it satisfies the condition such that d is positive and the second order partial with respect to x is positive as well. Let's go ahead and do that. And once we verify this, we can then determine what that minimum distance would be. So again, we're going to go back to our first order partials as we see here and write those out again. So here are our first order partials that we determined on the previous slide. Let's go back and just make sure. Here they are highlighted in blue. So now we're going to determine the second order partials to determine the value of d. So this will be the partial derivative of this with respect to x. That'll give us 20. The second order partial with respect to y would be positive 10. And then the mixed second order partial would be the partial derivative of this with respect to y. That'll be negative 12. Okay, so d is going to be equal to 20 times 10 minus negative 12 squared. It's going to be 200 minus 144, which is 56, which is positive. And then again, the second order partial with respect to x is also positive. So this does verify that we did find a relative minimum for our function. So that tells us that when x is 9/7, y is negative 6/7, and z is 3/7, we are minimizing the distance from the plane to the origin. So the last step is to determine what that minimum distance would be. So to determine that minimum distance, we do have to go back and use the distance formula between 2 points in space. So let's go ahead and perform the substitution. Remember, the second point was the origin. So we'll have 9/7 minus 0 squared, or just 9/7 squared, plus negative 6/7 minus 0 squared, and then 3/7 minus 0 squared. We can see our denominators are all going to be 49. Our numerators are going to be 81 plus 36 plus 9. It's going to be equal to the square root of 126 over 7. 126 simplifies to 3 square root 14. This is approximately 1.6. So this would be the minimum distance between the origin and the plane as we see here.